Hey everybody, this is Larry. This is day 12 of the July Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's bomb. 473 matchsticks to square. Hit the like button, hit the subscribe button, join me on Discord. Wait, did I say that right? Man, I'm not gonna lie. I'm a little bit off physically lately. As you know, the last couple of contests I've been just not great. The short story is not great. And today, yeah, we'll see how today goes. Sorry, friends, I'm just a little tired. All right, let's get started. Okay. So you're given an integer matchstick x with matrix of I is the length of the ith matchstick. You want to use all the matchstick to get one square. Should not break any stick, but you can link them up. Okay. All right. So I guess the first thing to do is, so total is equal to, just sum it up. And obviously if it's not equal to 0, we return false. And then the other case is if, maybe we want to sort it. We'll just, maybe we just get the max. And, so side is equal to total 4, because now these are all forced, right? Because you have to use every matchstick and you can't break them up. So this is going to be true. So then highest is equal to this. If highest is greater than side, we return false, right? So now we basically just go over the really hard cases, the obvious impossible cases. Let's take a look at the constraints. Okay. I was going to maybe actually play around some knapsack problem, to be honest, but seeing that each matchstick can be 10 to the 8, and in fact, does that go overflow? No, 15 times 10 to the 8 is okay. So it doesn't go overflow, but it is close. So there's no knapsack, but the other thing is that n is equal to 15, so we can do some sort of brute force, or not brute force, we can do some sort of, well, maybe brute force E, dynamic programming E solution. Okay. How do I do it? The naive thing that I was thinking of, the first thing is that, okay, each matchstick can be obviously in 4, in either of the 4 sides, and of course that's going to be 4 to the 15, and that's going to be too slow. That's 2 to the 30, which is a billion, right? So that's going to be too slow. What's another way of thinking about it? Well, I don't even. Maybe I could have just done this. Because I don't know that I'm going to use that again. Let's see. If we do some bitmask DP, that's going to be 3 to the 15 in one way, meaning that we try one side, and then we try to fill out one side, and then we try to do the second side, right? And then kind of so forth. And that's going to be 3 to the 15 times 4, or 3, I guess. But that's still too slow, right? What's 3 to the 15? 3 to the 15 is 14 million. So that's probably too slow in Python. Though maybe in other languages, maybe it's a little bit fast enough. Okay. Let's think about the naive case, right? So when we have a function that's can make, maybe you have sides left. I'm just going to say sides. Let's say we have a bit mask, and then we have the current sum, right? Yeah. Okay. I am going to do something a little bit funky, but we'll see. Okay, so in this case, what we do is just one at a time, right? So we want to start off by going return. Oh, sorry, I'm too used to my usual thing. We want to make. Let's see. We want to make. I was going to say we want to make 4 sides, but I already kind of alluded to this. The 4th side is forced anyway, so you can actually reduce this to just 3 sides using the current mask, which is none. Yeah. Because none of them. Oh, and just to go you know, this is kind of hard for a medium, isn't it? Huh? Maybe there's an obvious solution that I forgot. Maybe it's just brute forceable as well. But basically, a bit mask, you can think of it as returning to a. Sometimes I explain it the other way, but today I'm a little bit tired, as we talked about, and you can see that I'm a little bit dazed. But basically, the idea is that, okay, let's just say we have a scene set, right? Like basically, scene is equal to set, right? And then the idea is that, okay, let's say scene contains, you know, let's say 5 elements, right? The 0, we use the first one, we saw, you know, something like this, right? Because this is basically, let's say we've used the 0th matchstick, the 2nd matchstick, the 5th matchstick, the 7th matchstick, and the 9th matchstick, or I guess this is 0 index, so forgive me. And another way to write this, of course, is just by using, instead of using a set, because we know that this is going to have 15 elements, we can just write it as true, false, true, false, 0, 1, 2, 3, 4, false, true, false, true. Maybe I should have just used a smaller example, but nonetheless, 6, 9. So then the next one is true, right? And then false, say. I don't know. It doesn't matter, right? Because I'm too lazy to type out the full 15, but you get the idea. The idea is that this is the 0th index. This is the 2nd index. This is the 5th index, and then ... right? You could fill the 7 and then, okay, fine, right? 9, right? So that's basically the idea. And then you can also rewrite this now as TF, say, for 11 elements, or 12 elements actually, with 0 index, right? And of course, you can rewrite this as a binary thing: 1 0 1 0 0 1 0 1 0 1 0 0. This is just transforming the T to 1 and F to 0. And then lastly, this is, you can just convert this to a binary number, right? I'm not gonna do the math bit, but you know, that's basically the idea. And that's basically a very short story of what a bit mask is. I know that it can look confusing sometimes, but that's basically the idea. And there are just some operations like maybe like if 2 is in scene, that's the same as writing, you know, scene to 1 to the 2. Because now this is basically comparing some binary number with some other number that is, you know, something like this. So if they're both 1, this will return a non-zero. If one of them is 0, this will return 0, and that's basically the same as this. So that's kind of the idea behind it. I'm going to stop going over it now, but that's basically the idea about bit mask. Okay. But yeah, and then the current is obviously 0. I guess we could count up or count down, it doesn't matter. So maybe we'll just do side, and then we'll count down to 0. Okay. And then now we can, I guess that's just brute forcing, right? Okay. So now we go for I in range of n. We need to set up n. Man, my eyes are so tired. What have I done? Oh, I guess I now I remember. I'm not gonna lie. I played a lot of DDR earlier, and Dance Dance Revolution, in case anyone's curious. And I'm just like physically tired, and I didn't sleep enough last night. So yeah. Anyway, so if mask is not used, whoops. So this is what we said earlier. If this is non-zero, that means that if this is equal to 0, then we haven't used it yet. So then we can try current plus what's it, matchsticks of I, right? And we should do a few more things. Oh, this is minus because I subtract. And we have to check that n current is greater than or equal to matchsticks sub I. That will make sure that this is non-negative. And then here we go Oh, and then this just return true. Otherwise, we return false, right? And we have to do a base case, which is if okay, if current is equal to 0, then we can remove a side. So I'm just gonna have this to alias it. Otherwise, you can do some if statement here to kind of move that, but this is the way that I'm gonna do it. So then now we're back to side, right? Otherwise, if sides is equal to 0, that means we're done, because even though we have some left, it means that everything that's left is good. So then we return true. That, I think that should be good. Of course, we haven't done the memorization part, but let's spin it real quick. Okay, so that part is good. That I'm okay about. Let me see if I can think of a different case that is. Let's see. What is a good case? Let's just say 88844 maybe. I don't know. This could be. It's hard to come up with a case maybe. Yeah, so this looks good as well. It probably is a little bit slower, but something like that. But yeah, so that's gonna be good. So one thing that I would say is that this is deceptive, right? So okay, I think that I usually go over the analysis first, and this time I've kind of failed, so that's my fault. So size is equal to from 0 to from 3 to 0, 0 to 3, right? So that means that there's going to be 4 possibilities, though as we talked about, one of them doesn't really count because it's just always going to return true, so it doesn't really count. But so maybe there's just 3 possibilities, right? Why do we do this? What are we doing? Well, total time complexity is just equal to time per input times total inputs, right? So then now we're calculating what the total number of inputs are. Ref size, ref mask, it has at most 15. So for n is equal, so this is going to be 2 to the n, which means 2 to the 15, say. Up to, right? And why is that? Because n can be 15, and if you think about mask, each one of them can be binary, and that's just the number of binary combinations there are, right? Yeah, and then current is equal to here it could be from 0 to 10 to the 8. So naively, you're gonna ask, well, is this good enough? Because if you just do the math. Okay, so let's say we do this naively, right? So this is total number of inputs. Time per input is going to be O of n because of this loop, right? So yeah, or 15 maybe, depending on how you want to say it. So then total time is going to be, well, this is going to be constant. So let's just say this is constant. This is, let's just say this is t. So this is going to be O of 2 to the n, or n times 2 to the n times t, right? So that's our total time. And of course, given that t is 10 to the 8th, this is going to be way too much. But there's an observation that you can make. What is it? Well, we have 3 inputs, right, to this function, but one of them, actually, no, I'm lying, am I? I was going to say one of them is uniquely determined, but that's not even strictly true. Only one of them is uniquely determined, right? What do I mean by that? What I mean by that is this bit mask. What I mean by that is this bit mask uniquely determines the size and the current, right? What do I mean by that? That means that, I didn't really think about it that way. So that makes for a tighter analysis. I was going to actually, not gonna lie, I thought that size was going to be one of them. So it was going to be like 3 times n to the 2 times 2 to the n or something like this. But actually, it's even better than that, because basically, let's say, what I mean by uniquely determined is that, okay, let's say we have this mess, right? Let's say we have this mess. Well, and let's say that we used we use this one, we use this one, we use this one, and we use this one, right? Well, we can't, that's not a possible state actually. So let's just say we end up, okay, add a 5, right? Let's just say we use these 3, right? So your bit mask in this case would be roughly speaking 0 0 0 1 0 1 1, right? And you know, and that's fine. And what's current? Well, current, you can actually determine exactly from this, right? Because this is, the current is just each side minus, because it's always going to be close, the number that's closest to the multiple. Okay, maybe we'll do sides first. Maybe that's easier to explain. So sides, what is sides? Well, sides will have to be 1 if it has to get here, right? So side is equal to 1, or well, this is sides left, so this is actually 2 because we got 1 completed side. So then we only have 2 more sides to go, right? Yeah. And then current, in that case, I mean, I'm counting down, so the math is slightly more confusing. Sorry about that. In that case, this is going to be, you know, you reused 1 side, so that's 8. And then this side is going to be 3, right? And so what I mean here is that just strictly from the mask, you can figure out the other 2 things. Yeah. I mean, of course, we do, you know, there are some constraints that we put, which is current is equal to 0 and sides is equal to 0, and this, it's very nuanced to rewrite it without having these, but it doesn't even matter, right? So, okay, I'm gonna write the way that I intended to write it, and then I'm gonna make an optimization so that you can see that they're equivalent. But hopefully this explanation is good enough to get you to understand that, or not that you have trouble understand, is that I hope I explained it clearly enough that this is why, even though we look at these total inputs, it's not technically true because the number of unique inputs, we cross this out and we cross this out. So then now the number of total inputs is actually just unique input is this, right? And that means that now the new unique input is going to be 2 to the n times n. I actually thought there was going to be an S factor, but I forgot. Okay, that's pretty cool too. Right? And that's going to be total time. And we're going to write this in a weird way. I know that we usually write our, you know, for teaching purposes, I usually write my dynamic programming or memorization in a specific way. I'm still going to do that, the same style, but I'm going to make some observation, or like I'm going to make an optimization, or I wouldn't say optimization, but a code cleanup that shows you that everything is okay. Yeah. Wow. That is interesting. Okay. So it has cache is equal to force times 2 to the n. And then cache is equal to, it doesn't really matter, right? None times 2 to the n. And then here, literally, we just write has cache of mask is equal to true. Here we write cache of mask is equal to true. Cache of mask is equal to false. And of course, we have to do this other thing of using the cache, of course. If it has cache of mask, return cache of mask. And I think this should be good enough. Okay. I'm going to do a quick submit. Hopefully, I don't make any silly mistakes here. But hopefully, the explanation is good enough so far. And there we go, right? And again, maybe I have a pop-up blocker or something, but it's not showing up. 833-day streak, in case you're wondering. So yeah, so the reason why we only need to cache a subset of these is because the other 2 are uniquely determined by this. And there's another way you can write this actually as a result, right? So we can say that, okay, so yeah, so let's say we want to remove this just to prove that, you know, this is a good way to prove to yourself that's the way that I do it, right? Is kind of something like this. We want to remove this, right? Then how do we and we don't have to change most of the code because that's the beauty of it. We just use the mask. And then the idea here now then is, okay, we can actually calculate current and sides from this. That's what I mean. Current sides. And let's just say we have some total because it's not quite whatever, but so I'm about to sneeze. Achoo! 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 Excuse me. But yeah, but basically this is just saying, okay, if we used it, then let's get the total used so far, right? And then now, so current is just, I mean, we have to be really careful because we have to be really careful. I think that's the idea. Okay. I mean, yeah, but this is doable. It's just you have to be careful because if you don't do it correctly, some of the nuances in the constraint may be lost, meaning that you may have a stick that goes over to the next boundary of the next side if we're not careful, right? So yeah. So then current is equal to total mod mod side, right? It's actually side minus total mod sign. Is that true? Well, if current is equal to side, if current is, how do I say, is this right? Oh, and here we start at 0, of course. Because side is going to be, I guess this is right. I think this is right because if current is 0, we just skip ahead and also we have to remove this. But of course now we don't need this because current could never be 0. Because if this is the same, then now, yeah, I think this is right. And then sides is just you go to total minus, or not minus, but total over side is the number of completed sides. And then we just have, I don't know, 3 minus this, right? And that's basically it, I think. There could be a silly mistake here, actually, to be honest. Okay, and clearly there is because I'm returning true for everything. But like I said, so this is basically how or what a proof that they're equivalent, except for that I have a typo somewhere, or maybe not typo, but just a minor. I have to go through this a little bit. Okay, so so this is all the used ones. Okay, so this is used. So let's say we have each side. Let's say each side is 2, and we have 8. Right. So this is going to be 0, and then this is going to be, yeah. Okay. Did I miss something like this? So 8. Let's say we have 8, and then we have -2. If this is 3, then this is done. Okay. I mean, why is this wrong? I mean, I probably just have a very minor misunderstanding. It's either that or I wanted to count things that are used, not the things that are not used. So that's probably why I was just returning true, because my total is wrong. Whoops. Okay, there you go. And then we can submit again, and hopefully this is right. What a silly mistake, though. Yeah. I mean, this is much slower because we have to do this for loop, and this is why sometimes, you can use part of the input that doesn't use the input. You kind of do a running total, and you save a lot of calculation instead of this thing, which is why it's much slower. But the idea here isn't to optimize this per se, but it's to prove to you that both solutions, both this solution and this solution is equivalent, right? And that these two variables don't do anything. These two inputs don't do anything. And so the analysis is equal to this, which is here. Cool. Yeah, in terms of space, now, well, the space is way more easier to analyze now, right? Because now instead of having this 3D space, now you can do the mask and yeah, the time per space, space per input is O of 1. So this is just going to be O of 2 to the n space. Right. And that's pretty much all I have for this one. I know that this is a longer video, but I hope that some of these concepts about time analysis and uniquely determinedness, hopefully they kind of stick with you and hopefully they make sense. Cool. That's all I have for this one. This is all I have for today. Let me show you the top again, but this is pretty straightforward, I think. And here, and if you want the shorter result, you have this one at the bottom. Cool. That's all I have for this one. That's all I have for today. Like I said, stay good, stay healthy, take good mental health. I'll see you later and take care. Bye bye.